Alright, thanks. I'm Max. You can just call me Max. And today I'll be presenting on this project that I've been working on for the past year or so, actually almost exactly a year. And this is my new tracking system that I've developed called Tiny4FSK. So we'll get into that, but first, just a little bit about me. I've had the baby in this group. I've launched 9 balloons. I'm currently 13 years old. I'm a rising 8th grader. And I've started tinkering with electronics and programming since 1st grade. I got my first Arduino in 1st grade. And I've been avidly making and tinkering ever since then, creating useless projects and useful projects. And as you see here, I love sharing my knowledge. I teach classes, I present, as you see, and it's just kind of fascinated me. And I also love embedded system design, which is essentially designing PCBs and combining it with software to create systems. So let's go right into it. Tiny4FSK is my new tracking system that I designed. It is aimed to be lightweight and low power, and it uses Horus binary, which Mike was talking about in the last presentation. Which is kind of a relatively more modern system. And before I tell you more about why I built Tiny4FSK, I just wanted to say that Tiny4FSK is inspired by radio songs. And radio songs are great. They're robust, reliable, at least RS-41. However, for flights with smaller balloons and needing less gas, you kind of want it smaller and lighter, because as you get to bigger and heavier payloads, the cost can go up drastically. So I used to catch RS-41s and DFMs, and I still do, and we program them and fly them, and we still use them as our backup trackers. But now I designed my own alternative, which uses only one battery and is much smaller and lightweight. So many of the tracking systems that are on the market use APRS, some use LoRa, and I'm not really talking about pico balloons. This is more aimed for high altitude balloons as opposed to pico balloons. So most of the high altitude balloon tracking systems use APRS. And APRS, the Horus binary feature has a significant performance advantage to APRS, much higher link budget, and it's kind of more viable for this type of flight. So there aren't any Horus binary V2 tracking systems on the market today, which is why I designed Tiny4FSK. Another thing is that many of the tracking systems on the market are over $200, like light APRS some systems are $250. There are different versions that are slightly cheaper, but this board is only $30. And also, before I started this project, I didn't really know much about electronics. I designed a few APRS trackers that were big and clunky and never worked at high altitudes. And I wanted to get a much better experience with designing PCBs and making them actually work. So some of the main features on Tiny4FSK, it has a BME 280 environmental sensor, which harnesses temperature, pressure, humidity, and sends that along in the packet. It has a GPS receiver. Currently I'm using the U-Blox Max M10S. However, that's like $21. And we're shifting to the ATGM 336H, which is only $3. And yes, for those wondering, it can be configured for airborne mode and no power mode. It also uses an SI4063 transmitter, which is the same transmitter that the DFM-17 has, except this time it actually has a TCXL. So it doesn't drastically shift frequency, and it has a much larger frequency range, so you can send APRS on 2 meters if you want and have all the right hardware. As opposed to the Atmega 328P microcontroller, I'm using the SAMD21 to allow for much larger program space, because I have a little over 10,000 lines code which do not fit in the Atmega 320H. And the SAMD21 allows for much further expansion, and other people can expand the software a lot. And is powered with just one AA battery and can last from 15 to 19 hours, depending on how often you send the packets. And you can use the built-in AAA battery slot on the board, and that can last around 10 hours, 9 to 10 hours. So the way it works, a quick overview, it uses 4FSK, 4-frequency shift keying. For those who don't know, it modulates the signal based on shifting which frequency it's transmitting on. It sends just a static carrier tone and shifts the frequency it's transmitting on. Now it's modulating Horus binary V2, which is being transmitted on the 4FSK frequency. And it's a new protocol developed by Project Horus. I won't go too much into what it is because that's already been explained. And it uses CW to send the amateur radio call sign periodically. Now, one thing Horus binary V2 doesn't have is a legal call sign system, because over here the FCC doesn't allow lookup tables for the call sign. And the way the way Horus binary works is it uses, you can register for a call sign, and then an ID is given to you, and then the software like Horus DModlib it goes through the lookup table and matches it with a call sign and puts that onto SONTOB. However, you still need to send a amateur radio call sign, and I do that with Morse code, very small and simple message, and I post it every 10 minutes, but it can be configured. So for Horus binary, just a quick overview, it can extract the sensor data from the GPS sensor as well as the temperature, pressure, humidity sensor. Then it takes that and interleaves it with forward error correction. In this case, it uses the GOLE code, which can detect up to 7 errors and correct up to 3 errors. And it's the 23.7 code. Once it gets the GOLE code, it scrambles it and interleaves it. So when you're sending a packet over RF, you may get something called burst errors. So it's a bunch of errors in one place, which GOLE code isn't great with if it's all at the end of the packet. So that's why it interleaves the GOLE code between spots on the packet, and that will help get a much better forward error correction. Once it takes this packet, it encodes into the correct packet format and sends it along with the preamble. And this preamble allows the receiver to figure out which frequency the transmitter is transmitting on, and then from there it can decode the data. So here's a little bit more detailed guide about 4FSK. Essentially, it takes the encoded bytes and turns it into binary. So for example, if you have 1B, 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 which in this case is actually the preamble that sends along in the packet, if you take this and convert it into binary, it gives you this string. And from there, you convert it to symbols. So these two bits here in the binary, 0, 0, that translates to the symbol 0. 0, 1 translates to 1, 1, 0 to 2, and 1, 1 to 3. And there, so that's essentially just translating the binary into decimal, which is represented in the symbols. And each of those symbols is linked up to a frequency that's transmitting on. So symbol 0 is the first peak, symbol 2 is the second peak, and so on. So a big part of this project and the entire project is all a development phase, because there's endless improvements that you can do onto these projects. And it's a never-ending iteration cycle, so you build a prototype, iterate on it until you get a functioning prototype. Then you finalize the prototype, ship it out to people, and then find problems and iterate more by creating a new prototype, and so on and so forth, and it never ends.
Job security.
So you don't want to just design a PCB from scratch, not knowing if it's going to work or not. You design a breadboard. So breadboards are great prototyping tools. You just plug the wires into holes, and you can unplug and replug them. And they do come out, which allows you to easily debug problems and find problems, make problems, things like that. And that allows you to easily iterate on a prototype. The problem about breadboards is these are called through-hole, and you need a component that has through-hole pins. So these 2.54 millimeter header rows have to fit into the breadboard. However, all my components are SMD. I was able to find some alternatives, but I used a different radio module on the breadboard version, and I severely underestimated transferring the code from this radio module to the SI4063. And I also didn't include the boost converter because it's pretty hard to design on a breadboard. You have to have perfect connections, and there's a whole branch of PCB design related in switching boost converters. So for programming, you can make a breadboard prototype and get so the systematic way to do it is to get each module working, transfer data between them, and get each module working one by one on the breadboard. And then once you get working code for a single module, you combine it with another code for a different module. And then it all starts to come together into a functioning code. And the actual quick note, the Horus binary code I borrowed from Horus binary Radiolib, which is an example by VK5QI, which contains layer 2 Horus encoding algorithms by David Rowe, I think. I may have butchered the last name. However, I did eventually rewrite the Horus encoding system. It's not in the GitHub repository yet. It's still experimental. However, I did rewrite it. And then I iterated. So I use GitHub to version control my system. And this is a short screenshot of my GitHub commits, which is each time you send code to GitHub to store it on the database. And this is just a quick screenshot from that. And then I iterate, make updates until it works. Once I get my breadboard version working, I design a PCB. So breadboards, you obviously don't want to launch a big breadboard like this. That won't fly well. So I designed a PCB. So I paid for the PCB. I bought it through JLC PCB. And there's a nonprofit organization called Hack Club, which gives out free grants for high school students. And they have an onboard grant, which gives you $100 if you design a PCB board and document it. So I paid for the first batch of PCBs through that. And I got an open source hardware license. This is my UID. So that's in a database where people can easily look it up. And this is some screenshots. I use KiCad, which is the best PCB CAD system. You can't convince me otherwise. Free open source, huge community.
Of course it's the best, it's free.
Yep. This is a schematic, and then once you get the schematic, you transfer it to the PCB design. And then these are some of my revisions from my PCBs. This is my first revision. It's a dumpster fire. It's tons of different magnet wires, debugging, everything. It was a big mess. Version 2, I finally got some of the footprints right. I got the connections right. It kind of worked, kind of. There's still a few minor issues. Like I had no idea how to use chip antennas. I had a quick tutorial. The way you're supposed to use chip antennas is to take out all the copper from the layers underneath. And that creates a way for the GPS antenna to receive it from all directions, which I did not do on my first or second revision. On my third revision, I finally got it right and created a clearance, and it worked. This is really the functioning version right now, no known issues. There are a few awkward things, like the status LEDs are in a great place. The silk screen is horrible, which allows you to trace the footprints. This is my version 4. This has not been bought by JLC PCB yet, and I have not assembled this. This is from KiCad. It is going to be ordered soon. This is about the size of a gum stick, for reference. And it has expansion headers here, which you can snap off if you want to save on size and weight. And this is just a gallery of the development process. There's many different issues. This is called a debug probe. So you plug it into your microcontroller, and you can step by step through the code, change variables while it's running the code, stuff like that. And that definitely came in handy for a few pretty weird issues that I encountered. This is me soldering a board, assembling a board. Since I have like 0201s, 0402s, small footprints, I do something called a stencil and paste. So I laser cut the stencil out of Maya, which has holes for all the pads on the footprints. Squeeze a bunch of solder paste, which is essentially a paste form of solder. Then when you apply sufficient heat, it turns into the form of solder you're used to. So I squeegee it onto the stencil and then run a code, like a gift code for example. Just scrape it through the holes and it creates a nice even layer of solder paste. And then I just put that on a preheat plate and it melts all the solder evenly from the bottom. I do have 0201s and 0402s. This stencil, the arrow laser cutter isn't super high precision. So I did end up needing to hand solder the 0201s with a soldering iron, which isn't easy. I'm okay with 0402s, 06, 03s, and 08, 05s are fine. But 0201s get tricky, they fly off the board. And an SMD microscope definitely came in handy. You just put it under there, turn it on, and it gives you a screen from the microscope so you can see whatever you're doing, 4x zoom. This is my first revision, debugging. I needed to use a crystal because my TCXO didn't work. Configured it wrong as like a mirrored footprint. Here's me generating a packet from scratch. I was debugging a packet generation thing. Early version of the breadboard prototype. This is my debugging area, monitor with Horus GUI, transmitter. This is the first ever known picture of Tiny4FSK, small breadboard at Mega 328. I revamped it a lot. And then here's another picture of my home lab. So this is open source and free. So I documented it. So I have a GitHub repository. Sorry, my throat's getting scratchy. I have open sourced the code and I have extensive documentation here. You can take a picture if you want. I can show it again after. And since it's open source, I have a license. So for my software, I have the GNU GPL v3, and for my hardware, I have the certain Open Hardware License v2. So just give attribution, use the same license, and you're all good. So the current state of the project, everything works in testing. From a recent balloon flight, we weren't able to receive it throughout the entire flight. Because the SI-4063 transmit power isn't very well documented. So it's kind of guessing and checking on what output power level you're transmitting at. And I set the power level to 48 out of 127. So that was like less than a milliwatt. So we lost reception throughout this period of the flight. To prove it didn't turn off, here's the gap in the frame number, which is increased by 1 each packet and is transmitted along in the packet. And you can see that the gap, it shows it didn't turn off in between packets. And for reference, the green is an OS41 and the yellow is Tiny4FSK. So I have a pretty good GPS setup on the Tiny4FSK showing that it actually performed better than the OS41. And this is the GNSS satellites in view. So how many satellites it's locked onto to get the position. So some future plans for this project. Stress testing, obviously we're going to test it again tomorrow. If you're curious, watch W0MXX on Sontop Amateur. Range testing, because guessing and checking, it might not work this flight, the power may be too low. There may be underlying circuit issues, we'll see. Cold test, so throw it in a refrigerator and test it. That's because some of the components aren't very well rated. So there's more testing needed to do. And on this flight, it only went to 18 kilometers, which was intentional. We had a 150-gram balloon and a 100-gram payload. And then obviously more flights. Just throw some balloons up into the air, test as many times as possible, and get some good data. New modulations. I have all the hardware to do it. Why not actually do it? I'm not actually super limited to Horus binary because, once again, I have all the hardware. So I am planning at some point to incorporate APRS for those who aren't ready to move to Horus binary. Full CW integration, because right now it's only used for identification. I may be able to send along GPS coordinates along with it. That probably wouldn't be the primary tracking system. You'd probably combine it with something else. I am planning to incorporate VIDI, which is kind of a predecessor to Horus Binary. Project Horus used VIDI in the past before Horus Binary. And then I may incorporate LoRa. We'll see. I don't have a good chip to use it with. The SI4063 isn't meant for LoRa, although I might do it. We'll see. Shielding. So anyone who's used an Arduino knows that you can put shields onto it, which are headers aligned with the headers on the Arduino board, and it expands on components. So I have expansion headers. Solder on some header rows, put a board on top of it, and add on more functionality. And I just kind of want a little side note, some implications for Horus Binary. Tiny4FSK hopefully will build up interest in Horus Binary. And as Mike mentioned, there isn't a very large receive network. This is a screenshot from SonTub Amateur, and the green dots and the orange dots are receive stations. So you can see that there isn't full coverage over the nation, which, unlike APRS, which has built up so much interest as receive stations almost everywhere. And also making the Horus Binary protocol more accessible. Some people may live in areas which RS-41s can't get to, or other radiosondes. So this should be an option for people who don't have access to radiosondes. So I just wanted to do a live demo. See if it's still open. This is Horus GUI, for those who are wondering. I have it set, and I have it set to transmit every 15 seconds. So in a second now, we should start seeing, yep, there it is. We see a 4FSK signal. It just got decoded. And we have all the information here. And we can see it just uploaded to SonTub. And if we check on SonTub, here it is on SonTub. And Mike's also receiving it. I think that's everything. Thanks everyone for watching. I am also going to pass around the board. Pass it around. Yep. And the stack of. And then also, I just want to make a quick mention. My dad and I are co-founders of the New England Weather Balloon Society, and we operate out of New England, and we are a balloon society club with a big Discord server. We have a little over 100 members now, and we fly balloons together, recover radiosondes, track, and we have a large communication. So I'd like to pass some of these out. So just take a card and then pass the pile. And thanks everyone for watching. Now it's the time for questions.
So 2 questions. First, where can I buy one of your boards if I don't want to go through the effort of building it myself?
So the question was, where can I buy it? Right now I don't have a commercial shop. However, I am going to commercialize it in the future.
Okay, sure.
It's not quite ready for production. And yeah, does that answer your question?
I'll be looking forward to that because it looks like an awesome project.
All the design files are on GitHub, so if you do want to make the effort, you can order it through GLC.
And the other question, this is kind of for both you and Mike, but should we just work on like standardizing a Project Horus US frequency today? You know, should we just commit to something so we can have all these receivers be somewhat standardized?
So yeah, the question is, can we standardize the receive frequency? So actually one of the reasons why we can transmit with lower intervals on Horus Binary rather than APRS. APRS has 144.39. If you transmit more than a minute, people get angry. And with Horus Binary, we have such a wide transmit channel, which that means that we can transmit more often. Again, that means that it's harder to set up receive stations to receive everything on every frequency. So kind of the starting point idea that we have right now is to have a bunch of channels. Mike, correct me if I'm wrong. but having channels of standardized frequencies for each one. And then receivers can be tuned to specific channels, like channel 1, channel 2, so on.
Who's using it?
Yeah, and another thought that I had, as shipped out of the can from Horus, which is in Australia, I think it comes in a 431 point something frequency.
432.5. I think.
432.5, which in US ARRL band plan is in the ATF range, or ATV range, which most people say, nobody uses ATV, I don't care. My take is, we have an ARRL band plan, we should use it. And in the ARRL band plan, I looked and I thought 432.6 is in the middle of a low power beaconing section of the band plan, which seemed like what we're doing. So that's why all my stuff you'll see flying is going to be in the 432.5, 432.6 range. Some people who just want to grab the software and run it and say, well, I'm in ATV, who cares? And yeah, I can't do anything about that. So I would love to see more activity on that, but I think it's one of those everybody's got an opinion kind of thing. And I've got mine, and I voiced it to some people who are using different frequencies, and they heard my opinion and continued to do what they were doing. So I love the idea. I don't know if we could get momentum.
What's the process officially to do that with ARRL? Should this be approached with them?
Maybe. That might not be a bad idea. Again, one issue we have with Horus is that you do have to do either frequency coordination or time slotting. And APRS, has that issue. As we know here, we have so many APRS payloads in the air that we're doing time slotting very carefully. So it's still an issue even with APRS. But yeah, Bill, did you have something?
Yeah, what was the frequency that the Australian?
432.5, I think.
I may be wrong on that, but I
Okay.
think.
We generally use 434 megahertz, but it's a wide bandwidth, but it's like digital ATV is about 2 to 4 meg wide. Some groups are still using 439.25, but there's a push to move us into 434 on the band plan. So we're still active. I'm very active in ATV, and there's a group in the Midwest that's very active, and in California is very active, Southern California. But most of it is in the 1200 band and 2.4. But in the Midwest, it's 434, 439.25.
I was interested in inexpensive receiving systems. And I was thinking like a TT Go, where you put in multiple channels and then scan. That receiver isn't suitable for it anyway, but I did program the TT Go up to the 434, and the TT Go accepts it, but the receiver won't do the
4FSK.
But do something like that.
Yeah, definitely. I haven't played around with TT Go's yet. Trying to get my hands on one, haven't yet. But yeah, that's definitely an interesting idea.
I'll yell loudly and someone can repeat what I said, but you can, cheap Windows laptops are plentiful, and you could run the receive software on a cheap Windows laptop with an SDR. If you're Linux, not Linux literate, you could run Horus GUI on a cheap Windows laptop with an SDR. You might want to repeat that for the people at home.
So the answer to the question of C stations was cheap Windows laptop and SDR stick, and run the code there. I also assume we have the high version of it that is kind of the other standalone easy. Yeah,
Right there.
great. So the question I have is we heard in the earlier talk some of the challenges of that chip and the birdies and so forth. Do you have filtering on your board, or how is that being dealt with?
Yeah, so I do have a low-pass filter and a matching network, which is where all the O201s are built into my board. I haven't tested it a lot yet, however, it should work.
And you're slotting that for the 430 range?
Yeah,
Okay. Thank you.
no problem.
Impressive project.
Thank you.
good.